I'll be talking mainly about applications with Evosep ENO at high throughputs at 500 samples per day. Let me give you a brief overview. So once I got the Evosep ENO, I had a couple of benchmarking aims. So the first one was just a general check on its the high throughput capabilities, and similar to Ulysses, we did this on the Orbitrap Astral Zoom. So covering all of the standard methods from 30 to 500 samples per day at a 5 and 200 nanogram input with a commercial HeLa digest. And then we checked out how the 500 SPD method can handle more real sample by using our novel spec workflow for for cell lysats. And then, since that worked very well, we also went to phosphoproteomics at high throughputs, also some interactomics that we scaled up from Whisper 80 to now 500 SPD as well. And then at the end, I'll briefly touch upon the Evosep ENO on the new SAIX 8600 Xenotoph, but that's going to be more of a small preview. So without further ado, starting on the Orbitrap Astral Zoom, we did this benchmark with the same method for all gradients. So it's a fairly default method that we also used on the Orbitrap Astral, so 2 Thomson windows with 3 milliseconds max injection time. So it has a cycle time around 1.5 seconds, which is a bit too long for the short gradients, but nonetheless, it worked very well. So if you look here at the protein group IDs, so you can see the total IDs of a triplicate, not for a single replicate, but in the entire triplicate, as well as the cutoff for 20% CV on the protein group level. And as you can see, for long gradients, the IDs are quite high, up to 10,000 protein groups in a triplicate, and then they slowly go down, with the CVs being fairly good for the longer gradients, but a bit worse for the slower gradients, and also significantly worse for the lower input due to the limited sample amount. But what I'd like to highlight is that at 500 samples per day in a triplicate, you almost in total identify 8,000 protein groups, which is quite a lot. So a couple of years ago, this would have counted as a fairly deep proteome. And the reason is, as Nikolai explained earlier, and also Ulysses touched upon a bit, that back on the Evosep 1, there was quite some tailing and broader peaks for these shorter methods on the 500 SPD. So here on the right side, I've plotted the tick as well as the base peak chromatogram, and here a selection of 5 peptides over the gradient length. And if you compare this to the Evosep ENO, you see a very drastic difference for the peak shape, in particular for the tailing. So there's almost no tailing left here, as before you could see in some cases a very severe tailing. So thanks to this, we have now these very high protein group IDs, even at 2.2 minute gradient. But as the CVs are very high, I tried a few different methods, so mainly using variable windows that are designed around the precursor distribution. So starting with a slightly elevated 3 Thomson 6 millisecond method that has an even longer cycle time, you can get many IDs, but the percentage of the protein groups with a good CV are a bit unsatisfactory. That's because the cycle time of 1.5 seconds or even longer in this case is not giving enough data points per LC peak. So ideally we'd have a method that has only around 800 millisecond cycle time. And for this I had a very short method just with 50 windows and 5 milliseconds, which is a bit lacking in IDs due to the lower selectivity of a window. And then I went up all the way to 200 viral windows, and for the sweet spot at around 100 viral windows, I also increased injection time a bit, but unfortunately it didn't get much better. So if you look at the highest number of quantified protein groups with a slight gap, the 100 viral windows with 5 milliseconds injection time wins for the Orbitrap Astral Zoom, maybe there's another optimum between 100 and 100, around 150 variable windows, but this was good enough for me right now with around 80% or more than 80% of the protein groups with a CV below 20%. And with that, I moved to our new spec sample preparation method. Before I come to that, I'd like to briefly go over sample prep methods in general and what their limitations was. So in our lab, we have quite a long history with sample prep methods, starting at stop-and-go extraction tips or short stage tips. These basically just were used for cleanup in the beginning. Then the FAST protocol was developed in 2009, which allowed to do the entire sample prep, including digestion, molecular weight cutoff filters. But this was a bit slow and tough to handle sometimes. So we went back to stage tips and used them in the same way to perform the entire sample prep in the liquid volume of these stage tips. But here handling detergents was a bit annoying and could easily clog the tips. And the solution for that was a PARC protocol a few years later from the Olsen group, which was tolerant to detergents and had a straightforward sample preparation even at scale. But one limitation is if you try to scale this down to very low input, so if you go to 1 microgram or even lower, you start running into issues there. And the solution to handle these issues and still have a high throughput in a short time, we developed this SPEC protocol. So SPEC stands for solid phase extraction and capture. And I developed this together with my 2 colleagues, Dennis and Lucas. And there's also a preprint available on bioRxiv if you want to read the details. I'll briefly explain the principle. So you have these spec tips, which are in essence stage tips again, but instead of performing digests or any kind of manipulations in the liquid phase, we load the protein onto the solid phase. So in this little plug here, and once it's loaded there, we can wash the protein lysate or the sample and remove any harmful substances such as detergents, then perform the digestion and elute very clean peptides. Now, the question I ask myself is how well can we concentrate the proteins here? And in order to check this out, I labeled together with my 2 colleagues the protein lysate with fluorophore, labeled the enzyme with another fluorophore chemically on the lysines and N-termini. And if you look at these fluorescence images here after the equilibration step, you see that there's basically nothing on the tip. If you load the proteins, you can nicely see that here with a green color that the proteins are localized in the first 200 micrometers depth of the tip, so they get nicely concentrated. And if you add the enzyme to it and let it digest for a bit, you see that it's kind of in the same area. So here the different channels, the top one is green and the middle one is just the red one, and below the combined one, you can see that the overlap is pretty high. And if you elute, you also see that most of the green fluorescence is gone. There's just some traces in the background. Fortunately, the majority of the peptide, the enzymes, and presumably also undigested proteins stay on the tip, so they are safely removed. So the take-home message here is that the back tips confine enzymes and proteins in a volume of around 200 nanoliters, regardless of what the initial volume was, allowing to handle very small volumes efficiently and at a high speed. So since we can do this protein cleanup, the entire workflow is based on detergent-based lysis of whatever the sample is, which then gets transferred into a spec tip. In the most easiest scenario, this is just a C18 Evo tip. So even if you use 2% SDS or 2% SDC, you can actually wash it away with around 50% of organic, at least to the point that it doesn't harm the column and the chromatography afterwards. And yeah, after the peptide digest, the Evosep will elute it and analyze it. And this actually allows a very high throughput. Since the volume is very small, we can do this very fast. In order to get the most out of it, right now we actually use not C18 spec tips, but SAX spec tips because they are quite a bit more efficient, or they are easier to optimize. And in order to still use the Evotip, or rather to desalt, we load onto the Evotip directly from these spec tips by centrifuging. For this, we also have adapters in the 96 well plate format and actually also in 384 well plate format. But right now the 96 well plates are far more convenient because they directly fit to Evotips. And now the deciding question is, how fast does this protocol work? Well, we tried this with the 500 samples per day method. And you can see if you digest 200 nanograms of lysate, after 5 minutes, the digest is almost completely done, while the in solution digest in comparable conditions, so comparable pre-dilution, takes much longer. Like even after 2 hours, it's probably still significantly increasing. While with the spec protocol, after 60 minutes, also the CVs don't increase anymore. So that's our default digestion time now. So we can achieve complete digests within 60 minutes, which is very fast and goes well with high throughput applications. So we thought, why not pair this with the Evosep ENO at 500 SPD. And for this, we took an entire 96 well plate and digested K562 lysate on it. And as you can see, you get fairly consistent results. There's only one small dropout here, but for the others, you get almost always around 6,500 protein groups. And this is also reflected in very good median CVs for those protein groups of around 7.4%. And I have to note here that this was done with manually packed spec tips. So yeah, they are the largest source of variability. And even though this variability is there, we are still comparable to other more standardized, let's say, manufacturing protocols that are more standardized manufactured. So since this was working so well, we thought, why not also try phosphoproteomics? So my colleague Dennis is kind of an expert on this. He developed during his PhD this microphos protocol that scaled down the amounts required for enrichment to a 96 well plate format of around 1 to 20 microgram input. And as this can be done in 96 well plates, it's also fairly easy to do it in a higher throughput. And usually the LCMS analysis is a limiting factor. So back then, Dennis used 30 to 60 minute gradients, which were still considered short. But now we can do more than 100 SPD on the Evosep ENO with the arbitrary astral zoom. And if you just use 1 microgram of unstimulated K562 lysate at 100 SPD, you can get around 16K class 1 phosphosites per injection, which was very surprising. So keep in mind, if you have 2 different conditions in a triplicate, you usually get twice or almost twice the number of phosphosites you can see here. And while this did drop to around 9K with 200 SPD and around 6K for 300 SPD, 500 SPD actually maintained the same level as 300 SPD. And the CVs also were fairly similar. They were more dominated by the enrichment rather than the gradient. So they are all between 26 and a bit above 30%, which is not unusual for phosphoproteomics due to the enrichment step. And yeah, since this is working quite well, we are thinking about combining this with our new nanophos strategy. So this is another preprint that you can check out if you're interested. So basically it's using now, instead of the microphos protocol that is digesting in 96 well plates, we are using the spec workflow to prepare these samples and combining it with an automated phosphopeptide enrichment on the Agilent Bravo assay map. And then acquire on the arbitrary astral zoom. And yeah, this works very well even for very small amounts below 1 microgram. So up to 10 nanograms, we still get like a fairly decent, like up to 10,000 phosphosites even for an experiment. And hopefully we'll be able to combine this in high throughput applications as well. So this is still work in progress, but it seems very feasible now with Evosep ENO. And what also worked very well was interactomics. So this is from my colleague Andre and now also Luisa, who reinforced him last year. Basically, how this is done, you grow cells in 96D well plates and then transfer this lysate into another 96 well plate that's coated with a nanobody. And then you perform the pull down within this plate, digest in this plate, and from this plate you can then directly load onto Evotips. And this was initially run with a 21-minute sample per day gradient. So again, LCMS analysis was here the bottleneck. Couldn't be really scaled up that much faster without losing important binders. But now with Evosep ENO and the Astral Zoom, this is much more feasible. And here we'll show you a quick comparison to the Whisper 80 results on the timsTOF Ultra. So if you look at this here, the violet bars show you the number of known binders, so not the total number of binders, but just the known interactors of different genes. And well, as you would expect, on a longer gradient you find more, but you actually don't lose even weak binders if you go to shorter gradients with 200 SPD. It's just overall a bit less, so typically lower abundant proteins can get lost, but not necessarily, depending on how things go. And sometimes with shorter gradients you even get a higher number of interactors. This is also visualized here from left to right. You can see that for some proteins with a lot of interactors it can have a big negative impact, but for a lot of, let's say, the normal amount of interactors, you actually don't lose anything and you have the same amount of binders identified, even if you go from 80 samples per day to a 500 samples per day gradient. And I also have two examples here with two volcano plots, one for COX4L and the other one for EMC3. And you can see very nicely that even for weak binders with a small fold change, they are still identified with a very good FDR. So even weak binders can be preserved at these very short gradients. And last but not least, I'll touch upon running these 500 SPD gradient on the new CyX instrument, the 8600 Xenotoph. So this was launched just last week, and this is what the results look like for 500 SPD for different inputs. And it's also quite impressive. So at 20 nanograms, you can already identify 5,000 protein groups, but unfortunately the current software version I have has a bug for very high ion fluxes. So I'm not seeing the increase I should for 50 and 200 nanograms, but nonetheless, even for the 20 nanograms with 5,000 protein groups, this is pretty amazing. So once the bugs here are fixed, it can probably have similar results to the Astral, or close to the Astral, thanks to its CT scan mode, which is a very efficient scan mode compared to normal DA. So these black bars here kind of represent normal DA, while the red ones are for this CT scan, or scanning was how it was called earlier. And you can see that this is quite a substantial gain, and you also see this in the CV. So the quantification here is quite good. Usually the median CVs on the protein group level is below 10%, unless you run into this area where this kind of bug starts kicking in. But with CT scan, you actually get them even lower, thanks to more efficient scan acquisition at a shorter cycle time. And with that, I'm at my end, and I would like to draw a few conclusions. So the Evosep ENO significantly improves peak shape and peak capacity, and this is especially true for short gradients. And this makes 500 SPD now a viable option for high throughput applications at a good depth. So up to 7,000 protein groups can be identified from cell lysates. From just 1 microgram, we could still get 6,000 class 1 phosphosites, and pull downs basically could be scaled up without losing most of the biological information. So we preserved most of the information and just went up more than 5-fold in throughput. Of course, the best performance requires kind of these cutting edge mass specs, so such as the Orbitrap Astral Zoom or this new CyX instrument that can support very short cycle times with reasonable depth and dynamic range. And I'd like to thank my colleagues from the MAN lab, as well as our collaborators from Evosep, CyX and Thermo, and Jesper Olsen from the Olsen lab. And